presentation, and I must say I was a little awed to see the pairing that we have today in terms of both large spaces, where in my case this means chemical spaces, and the next talk will be more about large urban spaces. So hopefully some of the chemistry I'm going to talk about today is not too unfamiliar to the audience, but I'll do my best. So transition metal complexes are interesting and compelling materials because they consist of organic ligands with metal centers, and they can catalyze a series of reactions as well as act as functional materials in interesting ways. And in particular, their metal centers are really hard for us to have any intuitive understanding of how they're going to behave. And so first principles modeling is typically the way in which we try to go out and explore these spaces. And so in particular, we could think about trying to find the optimal, sorry, this isn't displaying correctly. We could try to think about identifying the optimal transition metal complex in this space, maybe to design a better battery, to design a better catalyst, but the right one for the job is going to depend on the particular application. And so we might want to think about, well, which atoms in particular matter most? And how can we accelerate this discovery on a computer? How can we leverage all of the advances in both artificial intelligence and in computational power to start to design these molecules from the ground up? And so we might think that for a certain property, the thing that matters most is the metal center, but we might also want to figure out how important it is to tailor the atoms directly in the environment of the metal, or maybe some properties are really going to depend on the overall structure of this molecule. And so the reason we should care about this is because these motifs keep showing up over and over again as some of the best atom economical and selective catalysts for conversion of abundant feedstocks into desired products. They're also prevalent in energy storage solutions and in the separation of toxic gases from air and so on with metal organic frameworks. And hopefully I'll touch upon all of these today. So our approach in accelerating chemistry with machine learning, I'll go over briefly just to give you a sense of what it is that we're doing and what is hard and what is easy. And so our group develops an open source code called MolSimplify. MolSimplify enables the generation of data of these transition metal complexes from first principles modeling with density functional theory. We've spent a lot of time thinking about representations, which are the way we represent the chemical problem to the machine learning models, and I'll get into a reason why we do that. Once we have both the data and the representations we want to pass to our models, we train a series of artificial neural networks. And then a key critical challenge is, how do we know when the trained artificial neural network is going to make an accurate prediction versus when it's trailed far away from where it should be applied? And so we do some development in what we call uncertainty quantification for that goal. And then once we know we have a model in hand, we have its uncertainty, we can either exploit the model and use it to make predictions very rapidly where it can be trusted on the order of seconds instead of the minutes or hours or days that traditional evaluation of properties would normally take. And we can also use it to go out and explore new regions of chemical space where the model might be uncertain, and then use that data in an iterative fashion to retrain our models. And that's called active learning, and I'll touch upon both of these today. But really, our ultimate goal is not just to make faster predictions over wider spaces, but to reveal design principles. How do we understand from searching these large spaces what it takes to make an optimal material? And I'll also talk about some of that today. So I mentioned in passing first principles modeling being an essential way to normally do this. So we need to generate data, and this is typically called high throughput screening, but the spaces I've been talking about are vast. So the number of ways we could think about permuting these atoms and representing them to a computer is very large. And in particular, there are extra knobs. So a lot of people talk about the small molecule organic universe of drug-like molecules and so on, but transition metal complexes inhabit an even larger space, in part because their metal centers can have different quantum mechanical spins. The metals that are of interest to us, such as first row transition metals, can be in a range of oxidation states. And so this motivates different choices in the trade-offs between how much data do we have, how much model complexity can we tolerate, and what way do we want to design our representation. So traditionally, in any machine learning approach, we want to balance our choices on these three axes. And specifically for carrying out accelerated discovery in transition metal chemical space, we need to think about distinct choices here. And so when we first got into this, our first goal was to imagine being able to predict the quantum mechanical ground state spin of a transition metal complex, as well as the energy splitting between that state and the next lowest state. And because we were going to be training this on first principles DFT data, which has its own challenges, we also wanted to predict how sensitive these results were to the exchange correlation functional. Because we have this high throughput workflow that assembles these complexes and makes predictions on them, we also wanted to not use as input any geometric information, but actually predict the strength of the metal ligand bond. And once we got this working on these first few properties, we naturally extended it to other properties I'll talk about today, including catalyst reaction energetics and redox potentials. And so the key thing to note is that because of the big size of these molecules, we work with relatively modest data sets, metals in multiple oxidation states and spin states. And we started out working with common ligands that an organic chemist or inorganic chemist would normally work with experimentally. And so we start with only a few thousand points. And so as a result, thinking about resolution of the representation turns out to be really important. It matters a lot how we represent our problem to a computer. And so the traditional way people were doing this is something very similar to how you would carry out a calculation on these molecules, which is represent all the information about all the atoms in the system equally, as well as what is their elemental identity. But there are a lot of heuristics in the context of transition metal chemistry that throw away almost all of that information and instead focus on the metal and its direct coordinating environment. So we had this idea that probably the right answer for developing a model that's accurate is somewhere between the two. It weights the information close to the metal center, but throws away a lot of information further away. And so that's where we focused our effort, was thinking about how could we improve these representations. And the first way we did this was just by chemical intuition and heuristics. So we wrote down a series of descriptors we thought mattered the most for transition metal chemistry, things like what is the metal center, what are its coordinating atoms around, what are differences in electronegativity around the coordinating atoms, and so on. And this was very heavily focused to what was going on at the metal center. And we picked these by trial and error. And the reason I still show these today is because it actually worked pretty well. But there are other properties such as the atomization energy that people sometimes want to predict. And that is a much more global all over property that depends on the number of atoms in the system. And we ultimately weren't that satisfied with this approach of choosing these ad hoc descriptors. We wanted to come up with a more systematic way to do this. And what we did was we went back to the literature and looked at something called Moreau-Brodo autocorrelation functions and developed an extension tailored for transition metal chemistry that we call revised autocorrelations. And what these are a series of heuristic properties that are tied to each elemental identity. And they have an adjustable depth. They're products and differences on the molecular graph. They can be centered on the ligand or centered on the metal. And we color code these properties as more electronic in nature if they depend on the nuclear charge or electronegativity, and more geometric if they depend on things like the number of bonds connected in the topology or the covalent radius. And all of the MCDL25 ad hoc descriptors have an analog in this rack set, but there are many more racks. And as we expand, if we follow through and write out these expressions, you can see that the racks, there are going to be more and more of them the further they are away from the metal. But the racks that encode proximal information only from the metal and immediate coordinating environment, we call proximal, and the ones that encode more information further away from the metal, we call distal. And so a principal component analysis in a whole molecule representation shows why doing this feature engineering is so important. So this is the adiabatic spin splitting that we want to predict. This is a quantum mechanical property of the complex. And you can see that what the whole molecule representation is doing is it's doing a really good job of clustering these molecules by size. And so two molecules that have 100 51 atoms and 37 atoms are sitting really far apart in the PCA in this whole molecule representation, but they have almost the same property that we want to predict, because this property is really dictated by what's going on near the metal. If we use a whole molecule, if we instead of a whole molecule representation, we use a local representation, you can see these 2 points are ending up much closer together. And as a result, we're making the model do a lot less work to reach the conclusion that these two materials are closely related to each other. As a result, on the same data set size, we can reduce the error in the model by an order of magnitude. And the result also is that we can correctly predict the quantum mechanical ground state spin in 97% of cases. The other cases are near degenerate. And you can see that in comparison to MCDL25, which is the ad hoc descriptor set we developed, these rack feature sets, either the full ones, which have 150 dimensions, or ones feature selected for the best 25 or so features, all do considerably better. They achieve near around 1 kilocal per mole mean absolute error with respect to the DFT reference. And that means that instead of spending hours or days to carry out the DFT calculation, we can get a result within about a second once this model is trained. And we can use this to do things like predict the geometries of these transition metal complexes, something which had been hard to do with even the best available force fields. And we can now cut those errors by an order of magnitude as well. But you might be wondering, what is different about these particular models in comparison, what is different about the rack models in comparison to MCDL25? And so here I'm going to color the features by proximal, middle, or distal. And you can see that the MCDL25 feature set is very heavily weighted towards proximal, what's going on in the immediate environment of the metal. And when we start with the full rack feature set, by definition of how those expressions work out, we start out with a lot of distal information. But if we apply this feature selection that I'm showing in the feature selection across a number of properties, so we call it URAC26, you can see that it ends up indeed very metal local with very little distal information. Both feature sets are in agreement that distal information doesn't matter very much. Where the difference arises and why the URAC approach gets better accuracy is because more intermediate information between proximal and distal is encoded. And so more than just making faster predictions, it's useful to see how we can obtain chemical insight over these large chemical spaces into what matters most to design a property. And so this is what I'm showing here. This is an abstraction on a porphyrin, but it refers to the most important features for predicting properties across data sets of a few thousand molecules. And I'm going to color the atoms blue if electronic properties matter more. I'm going to color them yellow if geometric properties matter more. I'm going to make the atoms big if they're important and small if they're unimportant. And so for spin splitting, what we learn is that exactly what I showed earlier is that crystal field theory or ligand field theory works. What matters most is the metal center and the electronic environment immediately around. But it gets interesting when we contrast this with other properties. For instance, to predict the bond length, that's a much more balanced property that depends not just on the two atoms involved in the chemical bond, but the environment around it, and both the electronics as well as the geometric information, for instance, how sterically crowded is the metal ligand bond. And then where things get really interesting is when we look at the redox potential, which lights up an entirely different part of the molecule. So now this gives us a sense that we can tailor the immediate metal environment to change its spin state, but we should change its size or shape or distant atoms to tune its redox potential. And I'll actually come back to that later in my talk. So this is what it looks like in a pie chart form, and I'm going to come back to these pie charts in a bit, but basically if you see more gray, that means more non-local information is important. If you see more blue, that means more metal local information is important. And so the elephant in the room so far is that everything I've been talking about depends on one density functional. And if you've ever run a density functional calculation, you'll know everyone has their own favorite density functional and that there's many, many of these possible functionals we could choose from. And so you might be worried that these pie charts I'm showing you are really just sensitive to which functional we chose. So we wanted to go back and ask, doesn't matter which exchange correlation functional we choose. And so here is a data set showing predicting that same property of the quantum mechanical spin splitting across a family of 23 different density functionals. And so some of these density functionals are often thought to be more accurate than others. For instance, the double hybrids cost a lot more to carry out. SCAN or TPSS are derived from much more first principles than these Minnesota functionals, but you can see almost all of these functionals are in really close agreement in terms of being correlated with each other. And when I say really close, something like TPSS versus BLIP, I mean really close. Even the ones where the correlations are lowest, we still see a lot of structure in the data. And so we can take a look at where these functionals are most likely to disagree. And you can see that these functionals are most likely to disagree in intermediate ligand field. So I'm showing a UMAP here in the latent space of a neural net I'm going to talk about in a moment, and see that the standard deviation of the ranking of these different complexes tends to be in really close agreement for the most extreme high spin or low spin points, but then disagrees in the middle. And we could ask ourselves, well, how do we approach consensus? How do we require that in order to predict something as a spin crossover complex, which means that they have this near degenerate spin state? If we ask what is a semi-local functional, which is a GGA, what does it predict will be a spin crossover, versus if we look at the class of functionals that were hybrids and we require all the hybrids to agree, then we look at the double hybrids, we can see that for spin crossover, in fact, depending on which family of functionals you have, the absolute prediction of the spin crossover property will depend on which functional you're using. And very little of the time will semi-local functionals agree with hybrids and so on. But this is really dependent on the property. We picked a really hard property to get the quantum mechanical spin state right with different DFT functionals. If we instead focus on something like the HOMO-LUMO gap, which is related to the optical properties of the molecule, then we see much better agreement across functionals. And so the degree of agreement for the raw property prediction is really sensitive to which property we're choosing. But I wanted to get back to the pie charts. And so here's an example of a pie chart I've been showing. This is the adiabatic spin splitting, and this is for the pure GGA BLIP functional. And this is how much the pie charts contrast for the HOMO-LUMO gap or the vertical ionization potential, both of which are relevant for, say, energy storage. And so we can switch over to a functional that had relatively weak correlation and ask ourselves, are the pie charts going to change as we change the functional? And what you can see is consistently, even when we look at functionals that didn't have that good correlation amongst each other, that the pie charts remain pretty consistent. The pie charts differ more between rows, so between properties, than they do by columns where we're changing the functional. And in fact, we can throw on here the PB0 double hybrid, which is a very costly way to compute the same property in comparison to BLIP. And what we can see is that the pie charts still are coming out to be almost the same. And so this gives us a way to go out and do low-cost chemical space exploration, build up that pie chart that tells us that design principle, and then go out and use a higher fidelity model to such as a double hybrid to then get these raw property predictions. And another thing we can do is we have 23 different density functionals. We can use a fine-tuning approach to train 23 different artificial neural networks and just ask ourselves, in a large space of 187,000 possible materials, where will at least half of these trained neural nets agree, and how does that differ from a neural net trained on just a single density functional? And so this is again the latent space coloring this 187,000 design space. And so this is the region that our consensus approach picks out as our candidate materials. If we instead chose a single ML model, we would get a much larger space than we get from the consensus approach, because it takes more to get the consensus. And then if we look at where do experimentally known spin crossover materials reside, they reside in a very close region, very similar to those in the consensus approach. And so as a result, while it's not guaranteed that requiring consensus among all the density functionals makes them more accurate, in practice, what we observe is that doing so means that we really hone in on the space where people know experimentally they can make these materials. And so this gives us a way of using imperfect models to reach a consensus agreement that is more predictive of experimental observations. And if we then ask, well, what are the materials identified by consensus but not yet experimentally screened? And we see that experimentalists tend to favor these iron nitrogen compounds for spin crossover, but our results suggest that cobalt nitrogen could be just as useful and interesting for spin crossover study. So I'd like to move on to talk about, how do we then use these design principles to design real world materials, and how do we address multifaceted design problems? And so the first way we decided to do this was to tackle redox flow battery, redox couple design. And in particular, we were thinking about designing redox couples for polar non-aqueous electrolytes. And so in that case, what we know is that people often use vanadium ACAC complexes, but these can be relatively easily oxidized or broken down. And so what we wanted to do is we wanted to address stability of the compounds, the resistance to the crossover between analyte and catholyte, make sure that this equation tells us that we need both a high concentration of redox couples as well as a high redox potential in order to maximize our energy density. So to address the question of stability and resistance to crossover, we built up a candidate pool that was comprised of fragments in easily synthesized materials that we combined in a very systematic way. And so, for instance, we started with heterocycles that show up frequently in synthetically accessible materials. We then fused them together up to 2 unique heterocycles to form 779 candidate core ligands. We added functional groups on the side with the idea that these different functional groups of varying size could tune the redox potential, since I mentioned that was a very non-local feature, as well as the solubility of the material. And then we combine these with 4 earth-abundant metals, which have not been as frequently studied as candidates for redox flow batteries. Putting these all together, you get the end result that there's around 2.8 million candidate materials. And these are all homoleptic transition metal complexes, and they're very large. They're about 100 to 200 atoms in size because we were focusing on stability and resistance to crossover. And as a result, these are really at the limit of what can easily be done with DFT. And so in order to address this simultaneous question of optimizing solubility and redox potential, we use something called 2D expected improvement and efficient global optimization. And so we're going to write down our 2 objectives. For solubility, we're going to focus on the log P as well as redox potential. And we're going to go out, and I'm showing a cartoon now, we're going to seek out DFT data on these points, and we're going to get a handful of points. We're going to train a neural net, then ask the neural net, what do you think of this 2.8 million complex space? And our goal is going to be to move new points past this optimal trade-off between solubility and redox potential, so past what we call the Pareto front. And so we're going to compute the expected improvement score, which is a combination of how likely these points are to go past the known Pareto front, as well as where is the model both uncertain. We're going to pull out candidates, go back to DFT, see how accurate we were, and then use this data to retrain the model. So this is what it looks like in practice. After a couple of weeks with DFT, these are all the points we get. We get around a couple hundred points. And this is really running full throttle on 64 GPUs. So this is a pretty serious enterprise because these molecules are so big. Then in a few minutes, we go back to the neural net. And we can draw the Pareto front on both of these graphs and see that where the front is lit up on the left graph, that's where we expect the improvement to be greatest, the EI score is highest. And so we cluster in that space and pull out representative points. Then we go back to DFT, and after about another week with DFT, we see that the model was not that predictive. Some of the points move the Pareto front forward, but many of them don't. So we go back to the neural net and ask it again, what do you think of this space? And after another few minutes, we can see that the front has shifted and the EI score has shifted. And this time we do a lot better. We get a lot of new points. And that's after another week with DFT. We go back to the neural net for another few minutes. DFT again, neural net for another few minutes. And then finally, after about 6 weeks with DFT, we see that we're reaching diminishing returns, and most of our points on the Pareto front are from the last 3 generations. The neural net is decreasing in its optimism that any of these points are going to significantly increase beyond the Pareto front. And so we can take a look at not just the fact that we've improved both of these properties, but what is on this Pareto front. And in particular, we see that there are some things in common, and especially if we don't want to sacrifice redox potential, while we're tuning the solubility, those compounds have in common that they have a manganese high spin center with oxygen coordinating atoms, sulfur in the ring, and small polar groups. The small polar groups are important to avoid sacrificing redox potential by making the molecule too big. And so some of these things we probably could have told you from our pie charts earlier, but this specific type of design with oxygen and sulfur in the ring is something no one had thought of before. And so we could ask ourselves, how much faster is this than just going out and randomly exploring the space? And we see that comparison to random search reveals at least 500-fold acceleration. And so maybe the first time I heard this 500-fold acceleration, I thought, oh, that's not very fast. Anyone can do something 500 times faster these days, until you realize it took us 6 weeks with full throttle DFT to get to that 500-fold acceleration. If you multiply 6 weeks by 500, you get around 5 decades. And so you can realize that this is the difference between having an answer in a month versus not in our lifetimes. And now we're readily extending this approach to catalysis and other challenges where this multi-objective optimization is essential. So I'd like to finish in the last part of my talk by talking about separations in metal organic framework materials. Metal organic frameworks are these combinations of molecular-like secondary building units that contain metal nodes combined with organic linkers that act like struts. And so they create these open pore frameworks with very precise crystalline structures. And they're widely used for gas storage, gas separation, as well as increasingly for catalysis, because they're really exquisite platforms on which we can think about designing both the shape and the accessibility of different molecular motifs in a metal organic framework. And so because gas separations is really the primary application of these types of materials, when we first got into this, most of the time people were trying to machine learn the properties of the materials. They focused on the characteristics of the pore geometry. And so we were interested to know if we could extend racks and apply racks to this machine learning and metal organic frameworks. And so what we did was we took advantage of the way MOFS scientists think about MOFS. And in particular, they think about the metal SBU, functional groups, and linker chemistry. And so we broke our MOF into those 3 domains and computed racks over each of those 3 domains, and then added them to the pore geometry features people typically use. And the result was that we improved the machine learning models for things like CO2 uptake. But more importantly, besides just prediction accuracy, I hope to this point I've impressed upon you thus far that we want to carry out feature analysis, figure out why the machine learning model is learning what it is. And so we can look at the ultra low pressure regime, and high pressure regime for 2 similar molecules that people often look at separations, and that's methane and CO2. And so what we can see is that in the ultra low pressure regime, the red, green, and purple parts of this pie chart tend to dominate, especially for CO2 more than methane. Methane just kind of behaves like a rock. And as we increase the pressure, we can see the blue portion taking over, especially for methane, up to high pressure, where you can imagine as we start to look at really high pressure uptake characteristics, just how many molecules you can shove in that pore takes over. So this gives us both a condition-dependent and molecule-dependent insight into what matters most for MOFs. However, depending on where we get the MOF data from, if we get it from experimentally characterized structures in something known as the core MOF database, or if we get them from hypothetically enumerated materials, we get different conclusions. And in particular, the core MOF experimental set tells us that what's going on at the metal SBU is really important for CO2 uptake, whereas these other hypothetical data sets seem to suggest it's a lot less important. So we wanted to know why. And so we broke down our MOFs into different domains, including the pore geometry, linker chemistry, metal, and functional groups. And what you're seeing here is t-SNEs of each of those different subsets of features. And we're coloring them if the hypothetical set, if a point is present in the hypothetical set, we're coloring them purple, red, blue, or green. If it's only present in the experimental set, you can see the gray shining through. And so for the most part, the sets are in agreement about pore geometry, linker chemistry, and functional groups, but where the biggest discrepancy shows up is in fact in the metal chemistry. There are many types of metal nodes that are present in the experimental set that just never have been hypothetically enumerated in these hypothetical sets. So it suggests that when we're creating these hypothetical spaces of materials to explore, they need to maintain the same realism and diversity that experimental sets have. And otherwise we're going to miss design principles. And so what we wanted to do is we wanted to go back to this core MOF database and see what else we could learn from it. So again, if you're not familiar with this, what this corresponds to is all of the MOFs that have ever been characterized with a single crystal XRD. Those MOFs have been deposited in the Cambridge Structural Database, and then they were further cleaned up and prepared so they would be ready for follow-on simulation or machine learning, and they're known as the core MOF database. And there's about 10,000 of these in here. And so what we did was we went back to these 10,000 MOFs in the latest version of the core MOF database, and we tried to featureize all of them. So we used the MOF recs I just described and tried to featureize them. Then what we can do is we can match those MOFs to papers. So they've been associated with papers through their CSD deposition, and we can download all those papers. We can download all the papers for which we can get a license to download them. And we can look into the papers with natural language processing and figure out if these MOFs are stable for solvent removal. That's one of the key things that you want to know about is how easily can we vacate the pores, because when you synthesize these materials, you end up with a lot of solvent molecules in the pores, and you need to eliminate them to use these MOFs for anything practical. And then the other thing is, at what temperature do they break down? So are these MOFs stable at high temperatures? And some of the critical key criticisms for using MOFs, say in applications of separations or catalysis, is that they're just not going to be stable in the real world conditions they need to be stable in, or they're not activatable. So these are two key criteria for an experimentalist to think about before they start to use these materials for a practical real world application. And this is something for which relatively few heuristics or any prior rules of thumb are known. These are things that usually the way that we have to figure them out is we have to go out and do the experiment, get the experimental result. It's also something for which me as a computational chemist, I wouldn't know how to set up a simulation that could really robustly predict the thermal stability of a MOF or whether the solvent could be removed. And so we're able to train machine learning models on these sets that we extract. So we extract the TGA, we extract the temperature of decomposition, as well as the solvent stability directly from the literature. And we train predictive models to predict activation stability. And if we look at the features selected in these models, say for classifying activation stability, we can see why why heuristics typically fail. So heuristics tend to focus on simple things like the metal node chemistry, but if we analyze much in analogy to that abstraction on the porphyrin, if we analyze the important features for predicting activation stability, we can see the linker chemistry really dominates. And this is not something people would have seen if they'd only studied a smaller subset of the MOFs or a single family of MOFs. Now, if we look at predicting thermal stability, we actually predict that to a mean absolute error of around 44C, the uncertainty in the measurements around 25C. So this is something that is subject to a lot of uncertainty and can be challenging to predict. But we do a reasonable job of predicting this decomposition temperature. And you can see that the map for what features matter most for predicting thermal stability are actually not that different from the activation stability. So it's unlikely we can make a thermally stable MOF without also making a solvent removal stable MOF. But that being said, what matters most is, again, the linker chemistry and a little bit more what's going on at the metal, especially its electronic features. And so what we can do is we can apply these two trained neural nets to the space of the materials for which we couldn't obtain the downloads previously. And there's about 1,500 points here that I'm showing, and we can make predictions in minutes on the 1,500 points that were not seen before. And we can use the uncertainty quantification I mentioned at the beginning of my talk to only make these predictions where we can really trust the ML models. And the result is that we get 1,500 new predictions of stable MOFs, orders of magnitude faster than we could have gotten them from doing an experiment. But another thing we might ask is, can we use these ML models to reveal strategies for redesigning the MOFs to be more stable? And so, for instance, a typical heuristic might have told us that if we wanted to make the solvent removal stability better, we could replace the zinc centers at the SBUs with calcium. Our ML models know that this won't do anything. So the solvent removal stability is the first score, and 1 means solvent stable. But if instead we focus on linker chemistry and remove this methoxy group sitting on the linker and add one linker that lacks that functional group, we can see that we can increase the solvent removal stability and also increase slightly the thermal stability when we combine that with replacing zinc with calcium. We could also look at specifically focusing on tailoring the thermal stability of an unstable MOF, unstable MOF according to its thermal stability. So most of our MOFs are stable up to at least 300 C. To be only stable up to 182 C is pretty poor thermal stability. And so here, what we could do is we could add fluorinated linkers. These fluorinated linkers have better electronic properties as predicted by our models. And so as a result, we can increase the thermal stability of this MOF. And these are things that can be validated by going into the literature and looking for the closest analogs. The other thing we can do, we've done, is we've taken these ML models and we've put them on a website that we encourage people to check out. It's called mofsimplify.mit.edu. And so you can take a look at visualizing any MOFs that you upload, as well as making predictions of the properties of the MOFs. You can look at what are the component linkers and SBUs of the MOFs. You can also take a look at the predicted thermal stability, where that thermal stability sits in our total data set, as well as how confident it is. And we also encourage user feedback, so users can give a rating to how they feel about how accurate our predictions are, as well as upload new data to help us refine our models. So I encourage you to check that out after my talk if you get a chance. But I'd just like to conclude now by saying we started by building tools that were open source for high throughput transition-melt chemistry to allow us to explore larger spaces. But just doing high throughput first principles modeling was never going to be fast enough to address these large scale spaces. So we also developed the first machine learning models to predict these very challenging to predict properties that are inherently quantum mechanical in nature, and thus few heuristics exist for them, such as predicting the quantum mechanical ground state spin. So we can now replace doing these tedious DFT calculations with machine learning model predictions, but just faster and more accurate model predictions is not really enough. We're really interested in using these models to accelerate discovery of new materials and ultimately reveal design rules and principles, what matters most about a material, which atoms matter most where. And all of our software and many of our machine learning models are available online, also via Conda and GitHub, as well as at a light web interface for either MolSimplify or MOFSimplify. And I'd just like to finish by acknowledging the students who did the work. MolSimplify was built initially by my first student, Timmy Anides, and the machine learning work in my group was pioneered by John Paul Janae. Current members of the group whose work I had the pleasure of telling you about today included Teacher Nandi, Chen Rudwan, John Marco Taronis, and I'd like to thank you for your attention and take any questions, assuming there's time.